Hello, I'm back. Happy New Year. I'd like to start off by first apologising for the radio silence from me for the last few months. The TLDR of it is that, well, work got really quite manic. I was running out of brain space by the time I got home from the office, and I've just been kind of going in circles with the ALU. So, the end result of that is that the ALU has actually taken a step backwards in terms of completeness. It used to be a fully functional working module, and now it isn't. I need to put it back the way it was. I'm going to try and be really quick about this, because I don't know how many times I've re-recorded this attempt at a video so far, and I just seem to be going nowhere. I'd also like to apologise for my sniffles, getting over a bit of a cold. Well, it's winter and it was bound to happen, so sorry about that. So this big old circle that I took the ALU in, what was the deal there? The deal is that I want to be able to add what are known as long numbers. Now, I'm going to specifically try not to go into what long numbers are right now, because I literally just 5 minutes ago tried to do an explanation of it, and I really need to prepare that, because I really suck at arithmetic, and for some reason I'm really bad at writing out and actually doing the binary addition when it's all written out. I always write 3's as 2's and 2's as 3's for some reason. I don't know. And it just gets me confused and makes for a not very coherent explanation. So I'm going to try and organise something a little better for that. But that's what I wanted to do. So in order to add long numbers, you need to do the addition on the lower half of the number. So let's just, for now, let's just say that a long number is a number that is greater than 255 and requires 2 bytes to represent it. You have the high byte. I always try and remember that the video is mirrored, so the high byte and the low byte. Okay, you do the low byte first and then you do the high byte. Why is that? Well, if the low byte overflows, just like the whatever it's called in the car, I can't remember, the little rolling meter thing that tells you how many miles or kilometers you've done. When it gets to all 9's, it's got nowhere to go except all the way back round to 0, right? But we just remember that it's done that once, or it's done that twice, or 3 times, or however many. And it's exactly the same thing with long addition on binary numbers. You have your base number, yeah, the lowest number, and then you have another number that counts the number of times that one rolled over. And then you have another number that counts the number of times that one rolled over, and so on and so forth, up to however big a number you want to be able to express. This is also particularly important when you want to be able to have signed numbers, because the range that you can express within a single byte or within a single word is half of what it would have been if it was an unsigned number. And more on that later. That's getting a bit C. So I was doing that, and I set up the ALU such that it would record the carry output from one operation and then automatically feed that in to the next operation. And that worked, and that was fine, and I was pleased with that up until I realised that I'd broken subtraction. How did I break subtraction? I absent-mindedly entirely forgot that in order to do the 2's complement you have to add 1, and I was using the initial carry input on the adder to do that, and I just hooked that input up to the stored carry flag. So in order to actually do a proper 2's complement subtraction, I would first need to ensure that the carry flag in the flags register was set, and then I'd tell the ALU, please do a subtraction, where it would then do the 1's complement. Again, I'm not going to go into that right now because that's a whole pile of theory that is very, very cool. I thought that when I initially learnt about this in college, in my computing course, I thought it made absolutely no sense and that it was just some kind of strange voodoo magic, which it kind of is. And I wasn't actually missing anything. It just is, it just works. Won't go into it. We'll do another video later, some other time, perhaps, if I can get my ass in gear. So I broke subtraction. I thought, bugger it. Okay, I need to redo all this again. And every time I come to redo a piece of logic, I think to myself, well, is there anything else I want to do while I'm here, while I'm rebuilding this? Because I don't want to be rebuilding the same thing over and over and over again. And that was perhaps my mistake, was that I went looking for work. And I realized that what I wanted to do, or what I thought I wanted to do, was to also add an increment, decrement, and not modes to the ALU. And I thought to myself, well, that would be really easy to do because they're not actually doing anything particularly new. In an increment is just an addition plus the constant 1. Decrement is a subtraction plus with the constant 1. Oh dear, the light's flickering a bit. Let's see if we can get that to stop. No, okay, never mind. There you go. And a not is just an XOR with the constant FF, or 8 ones, a fully on byte. And I thought, well, that's really easy because I don't need to build any new logic elements to it. I can use the ones I've already got. All I need to do is say, don't take the right-hand operand from the bus. Instead, just use a predefined constant which you can store on board on the ALU module. And that would add 3 new modes, and coincidentally I have 3 mode spaces essentially available because I'm using a 3-bit to 8-line decoder to decode the mode control word for the ALU, and I'm currently only using 5 of them. And I thought, oh, this is brilliant, okay, it fits, it all lines up, it's great, it was destiny, it was meant to be this way. As I started doing that, I was starting to realise that I probably wasn't going to have enough space on the ALU module to have all of that. Also, it made the wiring a little bit jaggedy, untidy, and it just didn't feel quite right. So I spent loads of time just sat there staring at it, umming and ahhing, trying to decide whether or not, or you know, what I'm doing and how I was going to go about this. And I came to the conclusion that actually it's not the ALU's responsibility to do either of those things. The clue is in that it is an 8-bit ALU, and yes, it could store the carry flag, so the 9th bit, and feed that into the next operation, but I would then be in the situation where, okay, either I have one add instruction that always takes the carry flag into account, so if you want to make sure that any subsequent adds aren't off by 1, you have to make sure that the carry flag is cleared before doing the add, and some chips do work like that. I'm not sure. I think maybe the 6502 does it that way, I think? I don't know. 6502 and Z80 do it in these 2 different ways, and I can't remember which is which, but anyway, you would need to clear the carry flag and then do your addition to make sure that you had a nice clean addition and you were going to get the correct answer, and you weren't going to get enough off by 1 error, which are so common in programming. The alternative is that you tell the ALU, okay, I would like you to do an add or an add with carry, which is generally used the mnemonics ADD and ADC, which no, I can't remember which is which. Z806502, that is. I thought, well, okay, that would require more modes going into a fourth bit. Is that right? Okay, well, let's say that that was the case, and I said add with carry. What's it going to do? It can't reach into the memory and get the next byte. I can't tell the ALU, right, you are going to be adding a 4-byte number, a 32-bit number. So that information is pretty useless to it. What's it going to do? Can't do anything. And with regards to increment, decrement, and not, the reason that I thought, oh yeah, I'll do that because that's going to be easy to do because they're not really doing anything new, they're just an application of what I've got, was actually the justification for why I shouldn't do it, in the ALU that is. Because they're not adding anything new. What they is a particular use case of the ALU. So, this stuff should probably happen outside of the ALU at the control matrix level. And that's what I've decided, that it's up to the control matrix to store the constants, and the control matrix can, by all means, decode an increment instruction, which will only require it to be given one register, and it has the constant that it needs, and it just goes ahead and does that. Or a not, again, it has the constant, it provides those to the ALU and says, there you go ALU, here is your input, give me the output. Oh look, that happens to be a not, but you didn't necessarily know that, you were just told to take this byte and XOR it with FF. You did that, you got the answer. I, as the control matrix, go, well, I know that that happens to be the equivalent of not, just inverting it. So I'm now putting it back the way it was. And just to show you, here it is, looking a bit sorry for itself, with the the bus buffer enable output lines flapping in the breeze because I haven't finished wiring it all together yet. So that's what's going on with the ALU. That is basically what I've been up to in the time between now and the last video. And yeah, it's essentially just taken me all this time to realise that I already was where I wanted to be, and the things that I thought I was adding to the ALU actually is the beginnings of the control matrix. So, oh well, at least I know that now. So yeah, that's 13 minutes on the video. I will just very quickly say that there has been bugger all progress on the memory module. In fact, I keep finding reasons why I want to tear it up and do something else, which I'm avoiding doing right now because it took long enough to do that. However, yeah, it's on those annoying breadboards with the split power rails. The little notches don't fit onto the others, which is also a bit annoying. And the colour of the wires, I'm finding reasons why they need to change. So, for instance, the white ones, again, are data bus, because white is data bus. And my initial thought was, well, I can just connect all these chips directly onto the data bus and just enable and disable the chip. That's fine. But what I then realised that I kind of wanted was to be able to see the value in memory at a particular address before it gets put onto the bus. I wanted to be able to preview it. And I can't do that if the chips are wired directly onto the bus. I need to use a buffer. So, for instance, one of these, the 74245s, to control whether or not it's actually being output onto the bus, and that way I can just tell the chips, yeah, always you can output, that's fine, but the chip, the SRAM chip under here is only outputting within this module. then there's another buffer that decides whether or not that gets output out of the module to the rest of the system. So yeah, there's that. The other thing is I've had an idea for something else I think I might quite like to build that would require SRAM chips. Can't decide if I want to use some of the ones that I've already got, these ones, and reduce the memory space of the module, or get some more SRAM chips, which can't hurt to have more SRAM chips, I guess, so I might just do that. I do like the idea of having a nice 16-bit memory address space. So there's that. And the very last thing that I have also been doing is just aesthetics and LEDs, because you can never have too many LEDs on a project such as this. So I've decided I'm going to ease up on the uniformity of all the LEDs, because so far I've been using exclusively these rectangular King Bright LEDs. I think they're 2mm diameter, so they can all sit immediately next to each other and produce these nice essentially bar displays, but without using the actual bar display LED modules that you can buy, because they have 10 LEDs in them and I want 8, and I'm a fussy bugger like that. So I was using exclusively those, but I really only have, well, I've got the 4 colours available to me, the red, the orange, the yellow and greens, which aren't on this one, they're on the ALU though. The only trouble is the reds and the oranges, they look almost indistinguishable when they're lit. You can only really see the difference when they're not. So I'm thinking, you know what, let's ease up, let's start using all kinds of different shapes and sizes and colours for all sorts of different things. So I bought a big old pack of various coloured 5mm round LEDs, and I found these nice 10mm diffused red-green bicolour LEDs, which are nice. So I think I'm going to start a convention of using these bicolour LEDs to show the enabled status of a particular control word, and then use some 5mm round ones next to it to show the value. So these these 2 LEDs here would show which register is selected, and whether or not this is red or green shows whether or not the word is essentially active or not. Green being active, red being inactive. In this case, they're all active low, so red is high and green is low. I've also been playing with transistors a little bit, as you can see on those LEDs, because so far I've just been powering the LEDs directly with the logic signal. So classic me, I'm not reading the data sheets until after I've banged my head against the wall for a few days. These logic chips, 74 series chips, they're not designed to source particularly high currents at all. So powering one LED off them is fine, that works about, and I'm not sure exactly what current I'm passing through the LEDs, but it should be around about 20-30 milliamps, something like that. And that's enough to power the LED and for other 74 series logic to see the high state. However, something that I'd noticed on the ALU module is where, say, on the adder subtractor down here, I have 2 yellow LEDs that both need to be lit at the same time, because one does the upper nibble, one does the lower nibble. And I was, again, using the same logic signal to power both of those, and they were both visibly dimmer than the rest. So I thought, okay, well, I'll start using transistors to switch the LEDs and not take so much current from the logic signal. Then the circuit for the LED is a very simple, straightforward, you know, VCC, LED, resistor, ground, or whatever way I happen to have built it at the time. And that works. That's pretty good. And I found that I could actually just bend the transistor legs around so that the base was on the outside and just pop them straight in, and that was fine, and it worked. And then I thought, oh, well, I'm doing well with this. Since I've got to implement a tiny little bit of logic here, in addition to the decoder, I thought, well, I've built a few gates using transistors before. Why not do that? Why not build it with transistors? And that was the point at which I realised just how little I actually know about transistors. The main thing being that for some reason I always thought that they were digital devices, that they're switches, or at least that's the way they were always presented to me, as transistors are digital, valves are analog, you know, but they're really not. They're not digital devices, they are analog devices, they're not switches, they're amplifiers. And anyone who tells you that they're a switch does not have your best interest at heart, because I found that very confusing. So I've been learning about transistors and the amplification gain on them and how to set what I want and make them work the way I need them to. I think for that particular instance, I'm going to say, sod it, just go back to using the regular old 74 series chips, just get the module working again and continue my transistor explorations on another breadboard, on another module somewhere else. So that's what I've been doing. And it also meant that I now know that all those transistors I inserted next to the buffers to brighten the LEDs don't have base resistors on them. So I'm not actually sure what's going on there, and I would absolutely love if anyone who's watching this video and has a bit of knowledge about transistors could post something in the comments, because this is, I don't know what's happening here. I don't know how much current is still passing through the base emitter junction in the transistor. So I've got the VCC up here to the collector, and the emitter goes down to the LED, and I've got my logic signal coming into the base. Now normally you would have a resistor here to limit the amount of current coming into the base, and that essentially sets the amplification, or sorry, not the amplification, but the amount of conductivity that the transistor will have, and the amount of current that will then be able to flow through the collector emitter junction. Now, in that case, what I've got is the signal coming into the base and then flowing down through the, coming out of the emitter and then into the LED and then into the resistor and then down to ground. So I think that the current is still being limited because my power supply isn't screaming at me, which it generally does. If I just, you know, have 5 volts going into the base and then the emitter going down to ground, it creates a dead short and it starts screaming at me and the transistor gets really, really hot. So I believe the current is still being limited, but I don't think it's having as much of an effect or as much of the desired effect as I had originally hoped it would. I suspect I do actually need those base resistors, and I don't think I really have the space in the current layout to put them there. So right now they're okay, and you know, nothing's blowing up. So I'll leave it as it is at the moment, but it's definitely something for me to consider going on. And yeah, please, if anyone could hazard a guess as to what's going on there, then please do. I realise that I should probably get on with the meter and try and conduct some experiments and see what's going on there, but I just haven't done that yet. So anyway, this is 25 minutes long now. I think that's about right. I think I'm happy with everything I've said in this video so far, so I'm going to call it a day there. And have a good one. And yeah, I'll try and post more regularly from now on. Bye.